Hello everybody, this is Schwab again. Today I would like to show you a very simple geometry to explain boundary conditions. In fact, I've prepared two geometries. One is, we call it left and right because we're looking at the coextrusion. So we'd like to study how two inlets merge and how they flow together, because the program can do coextrusion and we have to learn how to do coextrusion efficiently. First, I should say that each grid can have only one polymer, one material. So that is a limitation which we overcome by having multi-grids. So we can have two grids, one for each polymer, and we just multi-select them and solve them together. Now, if we solve them together, they are solved as one mesh. Of course, we have to solve what's at the interface between these two polymers and where is in fact the interface. Now, there are several scenarios which we can use. The first, most simple one is to assume that on that interface, on that boundary between them, there is a simple axis, right? See here, this is always an interface boundary condition, and we'll go to interface. At this particular example, I have the interface as axis. Now, of course, that can be used only if this is really straight and planar, because axis boundary conditions should have a straight and planar boundary. If you want to have a curved interface, you can still do that, but instead don't use axis and use wall, stationary, and use here adiabatic and treat it as an unconstrained slip. That means that the polymer can slide on that surface, and also the adiabatic says that the polymer will not be respecting the temperature, but it will get the temperature from the melt. So it's basically like an axis. But now this wall can be curved, which is the advantage. Well, our boundary here is planar, so we just can stick to our axis. Now we can see that we have changed in 6.9 the sequence of the or the order of the boundaries. Here I have the interfaces as a separate sub-items, and we see the axis, their interface in between. So we'll be discussing these three. So one of them is axis, as we've seen. If you put axis on the left, oh, I should do that. Axis on the left of this geometry, and also on the corresponding part on the right geometry here. Basically, these two geometries will be solved independent, so there won't be any difference if you multi-select them and run them together, or if you select one, solve it, and then run the other one and solve it. Why? Because these nodes are completely independent. They are not connected. There's no the degrees of freedom for velocity, pressure, temperature. They're simply separate for these two meshes. Well, this kind of solution gives us, of course, non-consistent pressures, and also it will give us non-consistent velocities. We can very easily see that now. You can see that I have checked all grids and global limits just to be able to set for both grids the same variable very fast, and I can see that on my velocity magnitude. And of course we see that one flow rate here, we have different flow rates. Flow rate number one is this one is 1 kilo, and the other one is 2 kilo. Okay, so this is the flow rate number 2, this is flow rate number 1, and we should see some flow across that boundary because we simply have higher flow rate. So you can study cases like this, and we also have different polymers here. If we look at the velocities at the exit, of course they don't match because, as I said, the pressures don't match, the velocity don't match. Simply they are treated independent, and the influence of one domain on the other one is just none here in this case, right? Now we can have another case, a different one, when we use a different boundary condition. So let me put back on this one the pressure so that we can compare. Right now, on this particular case here, we've used a different boundary condition. This boundary condition is again interface, but when we look now on the interface, we will see that we use a boundary called in between, right? This one here. Well, that boundary is meant just for coextrusion. What it does, basically, it says that the velocities will be matching, the degrees of freedom for velocity and also temperature will be matching. So that means that if you multi-select these two geometries, and if you solve them together, they will influence themselves. The problem is that the pressure does not, right? The pressure degrees of freedom are not depending on each other, so there is a discontinuity in pressure on the interface. So it is probably closer to reality because we see some velocities influencing, but we still don't have any flow across that boundary, okay? We only allow the polymer to slide on that boundary, similarly as we did with the axis, but now when the sliding from left and right are sort of being synchronized, so this is very close to reality. You see the velocity profile is very much as we would expect it probably, but the center should be in the middle, of course, right? Because why that would be on the side? So we can see that the velocity profile really indicates that the two streams influence themselves, but there is no cross flow across the boundary. So that is what the in-between boundary does. It is very useful situation. Let me put there back the pressure so that we have the same picture on these. And we have here one more, which is on the right picture here, on this one. And on this particular example, I again use the interface here. So if we go now to the boundary, we see that the interface now is a real interface, right? So I have a special boundary interface here. Well, that boundary says there can be crossflow. So that allows the polymer to cross from one grid to the other one. Basically, it does it by treating the degrees of freedom for velocity and pressure and temperature as identical for both grids. Now, that means that the polymer can flow across. That's what we would like to see in coextrusion, right? Now, in this case, of course, the pressure degrees of freedom match. And what more, if we look at the velocity magnitude, right, we'll see, okay, the velocity magnitude also here, and we also look at the velocity magnitude on this one here. So now we see that really we have, in this case, the velocity profile exactly as it is coming out from coextrusion, and we would see different polymers, would see, of course, different results, but that's the real case of coextrusion. So for the first time, the 3D FEM, our 3D FEM in virtual extrusion laboratory can do coex flows, and we see the polymer to cross the boundary. Now, we of course can look on things like cuts, right? So I can, let's say, show you what's inside, so we can do it for all the meshes because I have prepared those cuts here, and you can see that for the separated case where we had the axis in between, there's no flow across, right? Each polymer stays there, and basically if you solve them independent, you would see exactly this picture like with an axis boundary here. When we had the case where we had in between, you see there is some kind of, it's not really cross flow, but the two streams influence themselves because this one is flowing fast, it drags also the other polymer. So the mutual influence is really there, and the one polymer feels the dragging effect of the second polymer. However, we don't have the flow across as we need, right? If you would trace the particles, they will only go along that interface. Now, only in this case where we have really the interface boundary condition, we see that the polymer is crossing that boundary, the center is moving to the middle, and we really have a full coextrusion case. Now, also, if you would go to one of these boundaries and say, let's say that you'd like to integrate if you go to these boundaries and say, I would like to integrate how much material goes across that boundary, no flow rate across at all. There's 0. The same would be here. The only case where we really have non-zero flow across is here, 0.33 kilo across that boundary, right? So we have a crossflow here. Now, that is very interesting. Probably we could be tracing particles and doing cuts. The only problem is that when we do a cut or trace particle, or the particle hits that boundary, it cannot continue to the other grid. So in that case, probably the best would be just to create a copy of this left mesh and paste it here as a copy, called it merged, and now we can copy the right geometry for merge, right? And copy a paste from clipboard to this one. So now we have a merged grid, right? Which is from combined elements, and the advantage is that now I can put here again, let's say a velocity magnitude here, and I can treat it as a single mesh. So for me, if I just use a Z cut here and do some clipping and just at once, I will see simply both meshes, and now I finally see the real coextrusion, and I start to see the flow across, and I can see how these two interfaces merge and how they develop. I can see the elongation and all these effects, right? At the same time, of course, I can do tracing of particles. We can define a path line, let's say here. We click set. We can see that this seed is coming through boundary and goes to the second grid. We see the final point ends up on the left domain, so it really went across. Now we have to also be aware of one important thing, and that is that when these grids use different polymer, like the left one is using, for example, LLDP, the right one is using HDP, of course, when we do anything what is material specific, these grids will give us correct answer. For example, if I go to an integral and I integrate, I will get a correct mass flow rate coming across this boundary, right? If I go to the left one, I can get the integral too, which is 1.44. So that way I can easily find out what is the real flow rate. If I try to do that, however, on the merged grid, of course, it will give me a flow rate which is not correct. Why? Because he doesn't have two polymers. He can have only one. You see, there is only one HGP. The same is with the stresses. If you go to the left and right, they have correct stresses. So if you choose, let's say, a stress magnitude variable or shear, stress shear for the left and right, you see the correct stresses, and they don't match on the interface. We have different values from left and right. But if we go to the merged one, the stresses used are calculated from HDP. They are not calculated from LD and HD. So the merged layer does not know in which element we have which polymer. So whatever you do in post-processing for like particle tracing, that's correct. If you do cuts and look at velocities and the pressures, that's correct. But once you try to check the stresses, try to check anything what is material dependent, you have to be aware that that half which was using LDP is not correct. It's using wrong polymer. Okay. We can have different methods for solving coextrusion. We can use a separated with axis or a perfect slip wall. We can use in-between boundary, which is very close to reality. And the advantage is that we can do these calculations very fast and also easy post-process. Well, the real case of coextrusion is, of course, this one. So if we'd like to understand the coextrusion flows, we should use the interface in between. But also, I would really encourage you to use the axis or the perfect slip in case you'd like to just solve one polymer at a time, because we don't have to solve them together. Based on what you really need, you can choose one of these boundaries. Okay. Thank you for watching this video, and please welcome to watch the other parts of the boundary condition.